Наверное, свет стоит включить на всякий случай. Так, как там идет? Угу. Ну хорошо, тогда, наверное, можно. Okay, so let's recall that in the previous lecture we discussed the Gilfond transform for commutative Banach algebras. Well, let's recall the main ingredients of the construction. So first of all, for each commutative unital algebra, we can consider two sets. The first one is denoted by a hat, and it consists of all non-zero characters of A. That is, non-zero homomorphisms to the field of complex numbers. And the second set is the maximal spectrum of A, which consists of all maximal ideals. And we have an obvious map from the character space to the maximal spectrum, which takes each character to its kernel. In the general case, that is for arbitrary commutative unital algebras, we know that this map is always injective, but is not necessarily surjective. However, we proved that if A is a Banach algebra, that is a commutative unital Banach algebra, then this map is bijective. So we can identify the maximal spectrum and the character space. Next we topologize the space as follows. We recall that all characters are automatically continuous, so A hat becomes a subset of the dual space A star. We equip A star with the weak star topology, and we define the Gilfond topology on the spectrum to be the restriction of the weak star topology to A hat. And we prove that A hat is a compact Hausdorff topological space. This follows from the Banach law-glue theorem. So the maximal spectrum becomes a compact Hausdorff topological space, and now we define the Gilfond transform of A to be a map gamma from A to the algebra of continuous functions on the maximal spectrum. So this is a unital algebra homomorphism. It is defined as follows. It takes each element of our algebra, A, to a function A hat given by the following formula. So here we interpret little x as a character by using this identification, and we define A hat of x to be x of A. So we prove that gamma is actually indeed a continuous unital homomorphism between Banach algebras, and discussed some basic properties of this map. So this is the Gilfond transform. In general, the Gilfond transform is not surjective. This follows from some simple examples. For example, from some examples in exercise sheet 3. And in general, it is not injective. In fact, the kernel of the Gilfond transform is the Jacobson reticle. That is the intersection of all maximal ideals of A. And there are some simple examples of Banach algebras with non-trivial Jacobson reticle. So our main goal for today is to introduce a very important class of Banach algebras. Actually, probably this is the most important class of Banach algebras. And they are called C-star algebras. And our main result for today is the so-called Gilfond-Neimark theorem. Actually, there are two Gilfond-Neimark theorems, but we'll discuss only one of them. The first Gilfond-Neimark theorem, or the commutative Gilfond-Neimark theorem. And this result states that if A is a commutative unital C-star algebra, then the Gilfond transform is an isometric isomorphism between A and the algebra of continuous functions on the spectrum. Okay, so let's give some algebraic definitions. First of all, we suppose that A is an algebra, as usual over the complex numbers. And we define an involution on A to be a self-map from A to itself, which takes each element in our algebra to another element denoted by A star, such that the following axioms are satisfied. First of all, it is an involution in the usual set-theoretic sense. That is, if we apply it twice, then we get the identity map. Second, the involution should be antilinear in the following sense. Here, lambda and mu are complex numbers, and A and B are elements of our algebra. So the involution is antilinear. And finally, the involution should be a ring anti-homomorphism, in the sense that AB star is equal to B star A star. Okay, so such a map is called an involution on A, and an algebra equipped with an involution is called a star algebra. Star algebra. Okay, so far this is a pure algebraic object. Now let's put it into the context of functional analysis. So we define a Banach star algebra, to be a Banach algebra. Is a Banach algebra A, together with an involution such that the involution is isometric. The norm of A star is equal to the norm of A, together with an isometric involution. And now, probably the most important definition. We define a C star algebra, to be a Banach star algebra, a Banach star algebra A, such that the following identity holds. The norm of A star A equals the norm of A squared for all elements polygonal A in the algebra. And this identity is called the C star axiom, or the C star property. In Russian, we usually say C со звездочкой алгебра или C со звездой алгебра. Или C со звездой. Okay, so these are our main objects. Let's now introduce morphisms between them. Here we have two star algebras, A and B. Two star algebras. Then an algebra homomorphism, phi from A to B, is called a star homomorphism. Is a star homomorphism if it is compatible with involution. That is, if it commutes with the involution in this sense. And one more definition. You have a star algebra A and a subalgebra B of A. Then we say that B is a star subalgebra. B is a star subalgebra if it is stable under involution for any element little b in B. The element B star also belongs to B. So clearly a star subalgebra, any star subalgebra is a star algebra itself. And if now A is a Banach star algebra, then every closed star subalgebra of A is also a Banach star algebra. In particular, a closed star subalgebra of a C-star algebra is a C-star algebra itself. Okay, let's now look at some examples of C-star algebras. Of course, we always have a trivial example. The zero algebra is a C-star algebra for obvious reasons. And the field of complex numbers is also a C-star algebra. Well, the involution of the complex numbers is just the complex conjugation. And clearly all axioms are satisfied. Now a little bit more interesting example. If we take any set, X is a set, then the algebra of bounded functions, little L infinity of X, the algebra of bounded functions, well, we know that it is a Banach algebra for the supremum norm, but it is actually a C-star algebra. It's a C-star algebra. The involution here is just the pointwise complex conjugation. So this formula defines an involution, and this involution obviously satisfies all these conditions. So it is a C-star algebra. Well, now if X is a topological space, then we can consider the algebra CB of X of continuous bounded functions on X. And this algebra is a closed star subalgebra in L infinity of X. A closed star subalgebra of L infinity of X. And so it is a C-star algebra. It is a C-star algebra. An important special case is the case where X is compact. So in particular, if X is compact, then you see that C of X, the algebra of continuous functions on X, which is identical to CB of X, is a C-star algebra. And we will see soon that every commutative unit of C-star algebra is of this form. This will easily follow from the Gilfond-Neimark theorem. Well, another example of the same sort, you have a measure space, X mu is a measure space. Then we can consider the big L infinity algebra, L infinity of X mu. We know that this is a Banach algebra, but we can easily define an involution by the same formula as here, as the pointwise conjugation. It's easy to see that this is a C-star algebra. So the involution is given by the same formula as here. Well, so far all these examples are commutative. Now let's look at a non-commutative example, which is probably the most important example of a C-star algebra. If H is a Hilbert space, then B of H, the algebra of bounded operators, or bounded linear operators on H, is a C-star algebra. In this case, the involution is just the operation of taking the adjoint operator. And some time ago, when we discussed the adjoint operators on the Hilbert space, we proved that the operation of taking the adjoint satisfies all these conditions, including the C-star property. So this is a C-star algebra. And probably this example serves as the main motivation to consider abstract C-star algebras. By the way, this example easily produces another one, which is not unital. Namely, we can now consider the algebra of compact operators, K of H. And we know that this is a closed star ideal. Closed star ideal of B of H. So in particular, it is a closed star subalgebra, so it is a C-star algebra. And if H is infinite dimensional, then this algebra is not unital. Okay, let's also give a kind of a non-example, an example of a Banach star algebra which is not a C-star algebra. In fact, there are many such examples. Let's give only one of them. Well, an example and a little exercise at the same time. Let's look at the algebra Cn of AB of n times continuously differentiable functions on the closed interval of the real line. We know that this is a Banach algebra. This is a Banach algebra with respect to the following norm. So the standard norm on this algebra is the following sum from 0 to n. So for each k from 0 to n, we take the kth derivative of f, take the supremum norm, and divide by k factorial. So this is the standard norm on this algebra, and it is a simple exercise to show that it is a Banach algebra, because this norm is submultiplicative. Moreover, we can easily define an involution by the same formula as here, just the pointwise complex conjugation. So it is a Banach star algebra with respect to the same involution. But it is not a C-star algebra. Unless n is 0. If n is 0, then we come back to this example. This is just the algebra of continuous functions. But if n is greater than or equal to 1, then this is a Banach star algebra, but it is not a C-star algebra. So a simple calculation shows that the C-star axiom fails. Okay. Let's now introduce some more terminology. Again, we suppose that A is an arbitrary star algebra, and little a is an element of A. We say that A is self-adjoint or Hermitian if A star equals A. So we have already discussed such elements in the algebra B of H of bounded operators, but actually the definition works for any star algebra. More generally, we say that A is normal. A is normal if A commutes with A star. If our algebra is unital, if A is unital, then we say that an element little u in A is unitary if it is invertible. U is invertible, and the inverse of u inverse equals u star. Well, let's observe that clearly each self-adjoint element is normal. This is obvious. And it's also obvious that each unitary element is normal. And probably this is one of the main reasons to introduce normal elements. They are important because they generalize both self-adjoint and unitary elements. And another easy but useful observation is that for any element A in our algebra, the element A star A is self-adjoint. This is immediate from the axioms of the involution. Well, let's consider some examples which show how these notions behave in concrete cases. Example 1. Suppose that A is just the algebra of all complex valued functions on some set X. Or we can take the algebra of bounded functions on X, which is a C-star algebra according to this example. Or we can also take the algebra CB of X, where X is the topological space. So here X is a set. Or we can take CB of X, where X is a topological space. So in all cases, the involution is just the pointwise complex conjugation. It's clear from the definition that an element f of A is self-adjoint if and only if this function is real. F of X is real for each X. And it's also clear from the definition that f in A is unitary if and only if it is unimodular, in the sense that the absolute value of f of X is always 1. At this point, I must recall that we consider everything over the complex numbers. So of course, this doesn't imply that f is plus or minus 1. So such numbers form a circle on the complex plane. And in general, there are many continuous functions satisfying this condition. Another example is the algebra of bounded operators on the Hilbert space. Example 2. Suppose A is B of H, where H is a Hilbert space. Then an operator T on H is self-adjoint if and only if the inner product of Tx and y equals the inner product of x and Ty for each x and y in H. This is just the definition of this is immediate from the definition of the involution, because in the general case this is equal to the inner product of x and T star of y. So T is self-adjoint if and only if we have this equality. And another characterization, this is actually a little exercise for you, is that T is self-adjoint if and only if the following number, the inner product of Tx and x, which is sometimes called the quadratic form of the operator T, is real for each x in H. And there is also useful characterization of unitary operators. An operator U on H is unitary in the sense of this definition, if and only if it is bijective and preserves the inner product. This is also an exercise for you. Of course, the bijectivity it means just the invertibility here. And this condition can be written in the following explicit form. So U is unitary if and only if it is bijective and preserves the inner product. Okay, so if we look here and here, we see that somehow self-adjoint elements are related to real numbers. And morally, in the general case, it is very useful to consider self-adjoint elements as real elements, that is, as analog of real numbers. And the following simple result emphasizes this analogy. So we have the following proposition. For each element A in our algebra, there exists a unique pair of self-adjoint elements, unique pair BC of self-adjoint elements such that A equals B plus IC. So in some sense, B is the real part and C is the imaginary part of A. And the proof is very easy. We just give an explicit formula for B and C. This is B, and this is C. So clearly they are self-adjoint and satisfy this equality. And the uniqueness is a trivial exercise. Actually, if A can be written in this form, we can write the same formula for A star, then A star will be B minus IC, and we can just deduce these explicit expressions for B and C. And this implies the uniqueness. Okay, so of course these definitions and this proposition holds for any star algebra. So this is a pure algebraic result. Well, now let's come back to functional analysis and discuss some spectral properties of C-star algebras. First of all, we have the following result. Theorem 1. If A is a unital C-star algebra, and little a is a normal element of A, then the spectral radius of A is equal to the norm of A. Spectral radius of a normal element is equal to the norm. Well, some time ago, we proved this result for the algebra of bounded operators on a Hilbert space. And if we look again at the proof, then we can easily see that it works for any unital C-star algebra. So I'll not repeat it now, because it is identical to the proof for the algebra B over H. The same proof works for any unital C-star algebra. Well, let's now look at some corollaries of this result. Corollary 1, if A is a unital C-star algebra, then for any element little a, we have the following equality. The norm of A is the square root of the spectral radius of A star A. Well, indeed, the norm of A is the square root of the norm of A star A. This is just the C star axiom. But A star A is self-adjoint. In particular, it is normal. So the norm of this element, A star A, is equal to the spectral radius by theorem 1. And we get this result. So an important feature of this formula is that it expresses the norm in pure algebraic terms. This is the right-hand side of this formula is completely determined by the algebraic structure of A. It doesn't depend on the norm. And we see that the norm on a C-star algebra is uniquely determined by its algebraic structure. In other words, we can now state another corollary, which follows from this formula. Corollary 2, if A is a unital star algebra, then there is at most one norm on A, making A into a C-star algebra. I don't claim that such a norm always exists. This is not true. There are some examples of unital star algebras which cannot be made into a C-star algebra. But if such a norm exists, then it is unique. Or equivalently, we can say, each star homomorphism, each unital star isomorphism, between unital C-star algebras, is isometric. Each unital star isomorphism is automatically isometric because of the uniqueness of a C-star norm. In fact, we have a slightly more general result, corollary 3. Suppose that A is a unital Banach star algebra, and B is a unital C-star algebra. Then every unital star homomorphism phi from A to B is automatically continuous. It's continuous, and moreover, the norm of phi is less than or equal to 1. So this is another arithmetic continuity result. So we already know that all characters of a unital Banach algebra are continuous and satisfy this condition. And now we see that all unital star homomorphisms from a Banach star algebra to a C-star algebra are also continuous. To prove this result, we first of all look at self-adjoint elements. If little a is a self-adjoint element of A, then of course so is phi of A. Because phi is a star homomorphism, so it takes self-adjoint elements to self-adjoint elements. And so the norm of phi of A, the norm of phi of A, is equal to the spectral radius of phi of A by theorem 1. On the other hand, phi is a unital algebra homomorphism, and we know that unital homomorphisms reduce the spectrum. And in particular, they reduce the spectral radius. So we have the following inequality, which holds for any unital homomorphism. But the spectral radius of A is less than or equal to the norm of A. In general, we don't have equality here because A is not necessarily C-star algebra. This is a unital Banach star algebra. But in any case, you have this inequality. And we see that phi of A, the norm of phi of A, is less than or equal to the norm of A, provided that A is self-adjoint. And now let's extend this inequality to arbitrary elements, not necessarily self-adjoint, by using the following trick. We now take an arbitrary element little a in A. We look at the norm of phi of A, and we use the C-star identity, the C-star axiom, which gives us the following inequality. Now phi is a star homomorphism, so we can write this in the following form, because phi is a star homomorphism. And now A star A is self-adjoint. And for self-adjoint elements, we already have this inequality. So by the previous line, this is less than or equal to the norm of A star A. And this is less than or equal to the norm of A squared by the submultiplicativity of the norm. Of course, we use here that the involution is isometric. So this is less than or equal to the norm of A star multiplied by the norm of A, but this is just the norm of A squared. And that's it. So we take the square root, and we conclude that we have this inequality for any element in our algebra. And this completes the proof. Okay, another fundamental property of fundamental spectral property of C-star algebras is the following result. If A is a unital C-star algebra and little a is a self-adjoint element, then the spectrum of A is real. The spectrum of A is real. Well, again, just like in the case of theorem 1, we proved this result some time ago for the algebra of B of H of bounded operators on a Hilbert space. And if we look again at the proof, we see that the same proof works for any unital C-star algebra. So we just refer to the proof for B of H. Again, once again, this theorem stresses an analogy between self-adjoint elements and real numbers. the spectrum of any self-adjoint element is real. A useful corollary, corollary 1, is that any character of a unital C-star algebra is automatically a star character. So it is compatible with the involution. Each character chi of a unital C-star algebra A is a star character. To prove this result, again, we first of all we look at self-adjoint elements. If little a is a self-adjoint element, then we know that the spectrum is real. Spectrum of A is real. So now we take our character and observe that we may assume from the very beginning that chi is unital. We may assume that chi is unital, so it takes the identity of A to the identity in the complex numbers, just because otherwise it is 0. Otherwise it is identically 0. Well, we have already observed at the previous lecture that a non-zero character of a unital algebra is unital. So chi is a unital homomorphism, and so it reduces the spectrum. So this implies that the spectrum of chi of A is also real. But this is a spectrum calculated in the field of complex numbers. So this is a single point, just chi of A. So this inclusion means that chi of A is a real number. So we see now that if A is self-adjoint, then chi of A is real. If we now take an arbitrary element of our algebra, we can write it in the following form, B plus IC, where B and C are self-adjoint. Because of this observation, we see that chi of B and chi of C are, chi of B and chi of C are real numbers. So these are real numbers. And so, if we calculate chi of A star, so what is A star? A star is B star minus IC star, but B and C are self-adjoint, so A star is just B minus IC. B minus IC. So this is chi of B minus I chi of C. But since chi of B and chi of C are real, we can write this as follows. This is just the complex conjugate of chi of B plus I chi of C. But this is nothing but chi of A. And we see that chi preserves the involution. And this completes the proof. Another useful corollary of Theorem 2 is the spectral invariance of C-star subalgebras. So let's recall the following definition. Suppose that A is a unital algebra and B is a unital subalgebra of A, that is a subalgebra such that the identity of A belongs to B. So they have a common identity. And we say that B is spectrally invariant. B is spectrally invariant in A if for each element B in B we have the following equality. So the spectrum of this element calculated with respect to B is equal to the spectrum calculated with respect to A. So let's recall that in the general case this spectrum can be bigger. The spectrum calculated with respect to the smaller algebra can be bigger than this one. And if they are always the same, then we say that B is a spectral invariant subalgebra. Or equivalently, this means that we have the following equality, which means that if an element of B is invertible in A, then it is invertible already in B. And we now have the following corollary. Corollary 2. If A is a unital C-star algebra and B is a C-star subalgebra, that is a closed star subalgebra, containing the identity of A, then it is spectrally invariant. B is spectrally invariant in A. So what we want to do is to deduce this result from theorem 2. So let's take an element, little b, in the smaller algebra B, and suppose that B is invertible in A. So what we want to do is to show that B sits in here, so it is invertible in B. The first step is to consider the following self-adjoint element, B star B, and we observe that it has the same property, so it belongs to B. It is invertible in A, because both B and B star are invertible in A. And this element is self-adjoint. B star B is self-adjoint. So we apply theorem 2 and conclude that the spectrum of this element, and we now look at the spectrum with respect to B. B is a C-star algebra. So the spectrum is real. The spectrum is real. And this implies that if you take an arbitrary non-zero real number t, then the element B star B plus IT1 is invertible in B. Because minus t is not in the spectrum, minus IT, which is not real, is not in the spectrum. So this element is invertible. Okay, now let's now consider what happens when t goes to 0. Well, of course, this element converges to B star B as t goes to 0. On the other hand, we know that the operation of taking the inverse is continuous in any unital Banach algebra. So the inverse of this element goes to the inverse of B star B. This is true because all these elements are invertible in A. This element is invertible already in B. This element is invertible in A. So we have this convergence. But, so this element is invertible in B. So this element, the inverse of it, belongs to B. Because of this. And since B is closed, we conclude that this element also belongs to B. B star B inverse belongs to B. Okay, we now have the following obvious equality. B star B inverse, B star B, this is 1. This is clear. But on the other hand, we already know that this element is in B and this element is in B. So their product belongs to B. And so this implies that the element little b is left invertible in the algebra B. It has a left inverse in the same algebra. It is left invertible. This is not exactly what we wanted to show. We wanted to show that it is actually invertible. And we see that it is left invertible. Now to show that it is invertible, we can apply the same argument to the element BB star. And it's easy to see that the same argument applied to BB star, which is also self-adjoint, shows that B is right invertible. Little b is right invertible. It has a right inverse in B. But now it's an elementary exercise to show that if an element is left invertible and right invertible, then it is invertible. And this completes the proof. Okay, we are now almost ready to prove the Gilfond-Neimark theorem. Before we do it, let's recall the following fundamental result from general topology, namely the Stone-Weierstrass theorem. Suppose that X is a compact Hausdorff topological space. And suppose that A is a star subalgebra in C of X. A star subalgebra which contains the function which is identically 1. Yes, the identity of C of X, the function which is identically 1, belongs to A. The theorem states that if A separates the points, if A separates the points of X, then A is dense in C of X. So this is an important result from general topology. So we will use it without proof. By the way, sometimes in some courses of general topology, this result is proved only over the real numbers. So the real version of the Stone-Weierstrass theorem states that if A is a subalgebra in C of X from the algebra of continuous real valued functions on X, so this condition is now empty. This is just a subalgebra which contains the identity and separates the points, then it is dense. In the complex case, we also add this assumption. It should be a star subalgebra, and this is essential. Actually, the complex version of the Stone-Weierstrass theorem easily follows from the real version. So we must consider separately the real part of A and the complex part of A. And then they turned out to be dense. But the assumption that A is a star subalgebra is essential. We can easily construct an example of a subalgebra which is not a star subalgebra, which satisfies all these conditions, but which is not dense. So this assumption is essential here. Okay, now we are ready to prove the Gilfond-Neimark theorem. Suppose that A is a commutative unital C-star algebra. Then the Gilfond transform of A, which acts from A to the algebra of continuous functions on the maximal spectrum, is an isometric star isomorphism. An isometric star isomorphism. In particular, we see that each commutative unital C-star algebra is isometrically star isomorphic to the algebra of continuous functions on the compact Hausdorff topological space. So to prove this result, first of all, we show that gamma is a star homomorphism. It preserves the involution. So we take any element A in our algebra, and we take a point in the maximal spectrum, which is identified with the character space. So we look at the element gamma of A star, and we evaluate this function at x. So by the definition of the Gilfond transform, this is x evaluated at A star. We now apply corollary 1, which states that all characters are star characters. So by corollary 1, this is just x of A complex conjugate, or equivalently gamma of A star applied to x. And we conclude that gamma is a star homomorphism. Gamma is a star homomorphism. Actually, the fact that gamma is a star homomorphism is equivalent to the statement that all characters are star characters. So gamma is a star homomorphism, and clearly the image of a star homomorphism is a star subalgebra. So we conclude that gamma of A is a star subalgebra of the algebra of continuous functions on the maximal spectrum. And this subalgebra clearly satisfies the conditions of the Stone-Weierstrass theorem. So it is a star subalgebra. It contains the identity because gamma is a unital homomorphism, and it separates the points by the very definition of the Gilfond transform. You have two different points here, two distinct characters, say x1 and x2. Then for some A, x1 of A is not equal to x2 of A, because x1 and x2 are different elements of the same space. And so gamma of A separates the points. And we can apply the Stone-Weierstrass theorem, which implies that gamma of A is dense in the algebra of continuous functions. Okay, and let's now show that gamma is an isometry. To show that gamma is an isometry, again we start with a self-adjoint element. So for every self-adjoint element, A in A, the norm of gamma of A is equal to the spectral radius of A. This is just one of the properties of the Gilfond transform, which was proved at the previous lecture. So actually, this identity holds for any element in A. The norm of the Gilfond transform is equal to the spectral radius. But since A is assumed to be self-adjoint, we can apply theorem 1, which states that the norm of a normal element is equal to the spectral radius, and this is the norm of A. And we see that gamma is isometric on the set of self-adjoint elements. And if we now take an arbitrary element, we can apply the same old trick. We calculate the norm of gamma of A squared by using the C star property. So by the C star property, we have this equality. But we already know that gamma is a star homomorphism. Gamma is a star homomorphism, so we can write this in the following form. But now this element is self-adjoint, and we already know that gamma is isometric on the set of self-adjoint elements. So because this element is self-adjoint, we conclude that this is the norm of A star A. And applying again the C star property, we see that this is the norm of A squared. And we see that gamma is in isometry. Gamma is isometric. Okay, now to complete the proof, we observe that an isometric linear operator between Banach spaces has closed image. The image of gamma is closed. B, well, not on B, in C, in the algebra of continuous functions on the maximal spectrum. Just because it is complete. It is isometrically isomorphic to A, so it is complete, and the complete space is closed everywhere. So it is closed, but on the other hand, we already know that it is dense. It is dense and it is closed, so we conclude that gamma is surjective. And this completes the proof. It shows that gamma is an isometric star isomorphism. This one. Well, this is a part of a theorem which was proved at the previous lecture. First of all, we proved that the range of the Gilfond transform is a spectrum. And now by using this formula, we deduced that if you take the supremum of the points here and here, so the supremum here is the uniform norm of a hat. And the supremum of the absolute values of points in here is just the spectral radius. Okay. So this holds for any commutative unital Banach algebra. This is one of the basic properties of the Gilfond transform. So the point is that this is true for any element of any commutative Banach algebra. And the self-adjointness assumption is used here. So this is because of the self-adjointness of it. Okay, let's now look at useful category theoretic interpretation of the Gilfond-Neimark theorem. Let's consider the following two categories. The first category will be denoted like this. The objects of this category are compact Hausdorff topological spaces. And the morphisms are just continuous maps. The category of compact Hausdorff topological spaces. And the second category will be denoted by C_U C star. Here the objects will be commutative unital C star algebras. Well, the morphisms are unital star homomorphisms. Or I can say continuous unital star homomorphisms, but they are automatically continuous. We have already proved this today. So I can remove the word continuous here because they are continuous automatically. Okay, so these are our categories. And now let's construct two functors, or more exactly two contravariant functors. The first functor will be denoted by C. It acts from the category of compact Hausdorff topological spaces to the category of commutative unital C-star algebras. So to define our functor, we must explain how it acts on objects and how it acts on morphisms. The action of on the objects is very easy. It takes x to C of x, so the algebra of continuous functions, which is a commutative unital C-star algebra. And if we now have a continuous map F between compact spaces x and y, then our functor takes this map to the homomorphism which we have already met in the previous lecture. It is denoted by F dot. It acts from C of y to C of x by the following formula. So if g is a continuous function on y, then g composed with f will be a continuous function on x. And this rule defines a unital star homomorphism from C of y to C of x. So we get a contravariant functor from this category to this category. So this is the first functor, and the second functor acts in the opposite direction. It will be denoted by max. It acts from the category C U C star of commutative unital C star algebras to the category of compact Hausdorff topological spaces. So the action on the objects is again suggested by the notation. So it takes any commutative unital C star algebra A to the maximal spectrum of A. And to define the action on morphisms, we take morphism, unital star homomorphism, phi from A to B, and construct map phi star from the maximal spectrum of B to the maximal spectrum of A as follows. We identify these spectra with the respective character spaces, B hat and A hat, and define phi star as follows. So if chi is a character on B, then chi composed with phi is a character of A. The initial question is, why is it continuous? And it is continuous for the following reason. So this map, phi star, is nothing but the restriction of the dual map. Is the restriction of the dual operator, phi star, from B star to A star. And if we equip the dual spaces with the weak star topologies, then we know that the dual operator is always continuous. We discussed the continuity of this operator some time ago when we discussed the weak topologies. So this map is continuous, and of course the restriction of a continuous map is continuous. Okay, so we have two contrarian functors acting in the opposite directions. So we have the following picture. This is C, and this is max. So they are contravariant. For technical reasons, it is useful to make them into covariant functors. This is very easy. We just replace the category of compact spaces by the opposite category, by the dual category. So they become covariant functors. So I claim that they are equivalences of categories. And this is a category theoretic form of the Gilfond Neimark theorem. And moreover, they are quasi-inverse to each other in the sense that if we compose C and max, this functor is isomorphic to the identity functor on the category of compact spaces. Oh, sorry, on the category of commutative unital C-star algebras. And if we compose them as follows, max and C, this is the isomorphic to the identity functor on the dual of the category of compact spaces. So they are equivalences of categories. The proof is more or less immediate from the Gilfond-Neimark theorem and from what we already know. If we start with an arbitrary compact Hausdorff topological space X, we know that there is a canonical homeomorphism epsilon x from X to the maximal spectrum of C of X. So we know that this is a homomorphism, but in fact, all these homomorphisms are compatible to each other. And so all these homomorphisms give us a natural transformation. Is a natural transformation from the identity functor on the category of compact spaces to max composed with C. This is a little exercise to show that this is indeed a natural transformation. And the other way around, if we start with a commutative unital C-star algebra, for each commutative unital C-star algebra A, we have the Gilfond transform, gamma A, and we already know that this is an isometric star isomorphism. And again, it's easy to see that this is a natural transformation. From the identity functor on the category of commutative unital C-star algebras to C composed with max. And this completes the proof. So we see that if we go from left to right and then come back by max, then we get something which is isomorphic to the identity functor. And the other way around, if we go here and then come back here, then we get something isomorphic to the identity functor. This means exactly that these are equivalences of categories. In fact, this result is a perfect example of a complete duality between algebra and geometry. So this category is purely topological, and this is essentially algebraic. It's useful to compare this result with another similar result with the categorical form of Hilbert's Nullstellensatz, which gives us an equivalence between the category of affine algebraic varieties over the complex numbers and the category of commutative unital finitely generated algebras without nilpotence. All results of this type lead directly to non-commutative geometry. In fact, there are many types of non-commutative geometry. This is not just a field of mathematics. This is just a kind of ideology which unifies several different parts of non-commutative geometry, several related fields. And the fundamental principle of the functional analytic part of non-commutative geometry is that an arbitrary unital C-star algebra should be considered as the algebra of continuous functions on a non-commutative compact topological space. Well, this may seem paradoxical because no one knows what a non-commutative compact space is. Actually, we can define non-commutative compact topological spaces as objects dual of the category which is dual to the category of unital C-star algebras, not necessarily commutative. So this seems to be this doesn't seem to be a very deep statement, but in fact it is very useful. This principle is very useful, and it indeed leads to a deep and interesting theory with numerous applications and relations to neighboring fields of mathematics, such as K-theory, index theory, quantum group theory, and so on. Okay. Okay, probably that's all I wanted to tell you about the Gilfond-Neimark theorem. Maybe the last remark, the final remark, is about the non-unital case. Just a few words. So in this course, we're all interested only in unital algebras because of their applications to spectral theory. But sometimes it is very useful to consider non-unital C-star algebras also. And in the non-unital case, the difference is as follows. We still have two sets for each not necessarily unital commutative Banach algebra, the character space and the maximal spectrum. The character space is still the set of all non-zero characters. But the maximal spectrum is defined in a slightly different way. It is the set of all maximal modular ideals. Modular means that the quotient of a modulo such an ideal is unital. It turns out that if A is non-unital, then we should consider only modular ideals. And we still have a bijection between A hat, between the set of characters, and the maximal spectrum, the set of all maximal modular ideals. So this is true for any commutative Banach algebra, not necessarily unital. Next, we topologize a hat in the same way as in the unital case. But in contrast to the unital case, it is no longer compact, it is only locally compact. Locally compact and Hausdorff. And finally, the Gilfond transform of A is defined in much the same way as in the unital case. Actually, it is defined exactly as in the unital case. But now we can say more. The image of this map is contained in the algebra of those continuous functions which vanish at infinity. This means that for each epsilon, there is a compact set K in our space, in the maximal spectrum, such that our function A hat is less than epsilon outside K. So this property means that A hat vanishes at infinity, and it turns out that the image of the Gilfond transform is contained here. Of course, in the unital case, this is just the algebra of all continuous functions. But in the non-unital case, this space is not compact, so this assumption is essential. This property is essential here. So this works for any commutative Banach algebra. And we have the non-unital version of the Gilfond-Neimark theorem, which states that if A is a commutative C-star algebra, not necessarily unital, but commutative, then the Gilfond transform is still an isometric star isomorphism. So, modulo these modifications of the Gilfond theory extends to the non-unital case. Okay, so that's all for today. At the next lecture, we introduce continuous functional calculus in C-star algebras, and then we apply all these machinery to the spectral theory of operators on Hilbert space.